new Green Chemistry Education webinar series by the Green Chemistry Commitment. My name is Amy Cannon. I'm the Executive Director of Beyond Benign, a nonprofit organization dedicated to green chemistry education. The webinar series is designed to highlight relevant topics in green chemistry education for faculty and students. Our goal is to provide resources for faculty and students who are looking to adopt green chemistry into their courses and programs. So thank you all for tuning in. I know we have a great group of people who have signed up for this, and I know a couple of colleges and universities that have groups of students that are listening in. I know specifically at Bridgewater State and Salem State. So welcome to all of you. With that, I'm going to give you just a little bit of background information before we get going. We're broadcasting live and recording this session. Therefore, all attendees are in listen-only mode and all the lines are muted. So if you have a question at any time during the webinar, please type it into the question box that's located there on your control panel. And we're going to try to answer as many of the questions as we can after Dr. Warner's presentation. So please just feel free to type them in at any point. The webinar is being recorded, as I said, and the recording will be posted on the link that you see here on our slide and also in the welcome message on the control panel. So any supporting documents, such as the presentation slides and any additional materials, will also be posted at that link, so feel free to go and check there. And that's where you'll also be able to find information about upcoming webinars. The webinar series is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, growing departmental resources for those looking to adopt green chemistry, improving connections to industry, and affecting systemic change in chemistry education. The program is a voluntary, flexible program for adopting green chemistry student learning objectives and for promoting the work that you're currently doing at your institution that can serve as models for other institutions to get involved with green chemistry. So you can find more information at the link that you see here, greenchemistrycommitment.org, or you can also email me directly at amy_cannon@beyondbenign.org. So as part of the webinar series, we're paying tribute to an inspirational leader in the field of green chemistry who passed away at the end of last year, Dr. Al Matlack. Dr. Matlack was a researcher spending his career at Hercules and DuPont. He was an educator at the University of Delaware and an author. He authored the first comprehensive textbook on green chemistry in 2001 called An Introduction to Green Chemistry. His family donated several copies of his second edition book. They were personal copies of his, which was published in 2010. And we will be giving away a copy of the textbook to one webinar participant during each of the first several webinars. So we will announce the randomly selected winner from our list of attendees at the end of the webinar, and we will send the textbook directly to you. So you'll receive a follow-up email, and we'll request your contact information so we can get it right to you. Okay, with that, I'd like to introduce our webinar speaker, Dr. John Warner, to help us kick off this Green Chemistry Education webinar series. So John is the recipient of the 2014 Perkin Medal, widely acknowledged as the highest honor in American industrial chemistry. He received his BS in chemistry from UMass Boston and his PhD in chemistry from Princeton University. After working at the Polaroid Corporation for nearly a decade, he then served as tenured full professor at UMass Boston and Lowell. In 2007, he founded the Warner Babcock Institute for Green Chemistry, a research organization developing green chemistry technologies, where he serves as president and chief technology officer. And he also founded Beyond Benign, a nonprofit dedicated to sustainability and green chemistry education. He's one of the founders of the field of green chemistry, co-authoring the defining book, Green Chemistry Theory and Practice with Paul Anastas. He's published over 200 patents, papers, and books. His recent work in the field of pharmaceuticals, personal care products, solar energy, and construction and paving materials are examples of how green chemistry principles can be immediately incorporated into commercially relevant applications. So he's received numerous awards, including the 2004 Presidential Award for Excellence in Science Mentoring, the American Institute of Chemistry's Northeast Division's Distinguished Chemist of the Year, the Council of Science Society President's 2008 Leadership Award. He was named by ISIS as one of the most influential people impacting the global chemical industries. And in 2011, he was elected a Fellow of the American Chemical Society and named one of the 25 visionaries changing the world by Utley Reader. So John will discuss the future of chemistry education and the role of green chemistry in that future, and he's also going to answer any questions from the audience and help us kick off this the first webinar of this new Green Chemistry Education webinar series. So with that, I'm going to hand the controls over to John.
Hello all. I don't know if this is working or not. Are we up and running?
Looks great.
Excellent. Well, thank you, Amy, and welcome everybody to this webinar. I hope I do a good job kicking this off. I want to immediately start with a disclaimer, and as nice as it was for Amy to say I'm going to be discussing the future of the chemical education enterprises, I am not. I am completely, that would be very presumptuous of me to believe that I have any gifted insight into what the future holds. I do not. But, I am about to talk about here, I want to be very, very clear, is not me sitting on a box telling the world what the world should do. We have far too many people telling each other what they should do. I'm just focused on what I can do to help and what and I think everyone needs to really look at their own world and what they want and what they can do and not worry too much about what other people are doing. So I am not in any way telling anybody what they should do. However, I have, I'm going to be 52 in a couple weeks. I've lived on this earth for a long time. I've worked in industry at Polaroid for 10 years and saw how the chemical industry works. I worked in academia for 11 years, saw how academia works. I've got over 250 patents and publications. I've co-founded a small company and 2 small companies, and from an entrepreneurial perspective, and I've been active in green chemistry policy with the US EPA, California, and Massachusetts. So my life has given me the opportunity to see how we do chemistry, how we teach chemistry, how we invent chemistry, how we invest in chemistry, and how we manage chemistry. That this doesn't make me an expert in any of these fields, and there are people who are far more knowledgeable in every one of them. So what I'm going to be presenting is the way that I see it and what works for me and how I put that together. So please don't interpret me as being presumptuous that I have any gifted insight. This is what works with me, and for us to truly achieve a sustainable future, we must have a free forum of interaction of ideas that we can share. And if anything I have to say has any value that you want to embrace, please do. And if not, that's great. Send me an email. Let's have a conversation if you're interested in. But I have no need or desire to get you to agree with me. This is the way that I look at the world. So today's talk, I'm going to go through each of those with a specific emphasis from my perspective on how education obviously is central to all of this, and how our students in chemistry education, some of our students are going to ultimately become chemists, but many of them are not. Many of them are going to go off into other fields and do different aspects of chemistry. And if we accept that we need to change things to get on a path of a sustainable future, it's not just changing how we do chemistry. It's not just changing how we teach. We've also got to look at inventing, investing, and managing. And that's where we as educators have an excellent opportunity to present our students with different ideas to reflect not just the people that are, in the hoods pouring beakers and flasks, but everyone in society, whether you're a consumer, whether you're a voter, whether you're a manager, whether in whatever aspect of life that you are, there's a certain role to play in chemistry, and we need to do a better job at communicating the centrality of chemistry in this discussion. So let's first start with doing chemistry. As you've heard in the introduction, and anyone who's heard me speak before knows, I worked at Polaroid right out of graduate school, so I was trained as a medicinal chemist and then jumped feet first into a manufacturing chemical company. And kind of like a deer in a headlight, it was like, what am I going to do? And I really started to reflect upon the chemical industry back in the late 80s and how we do stuff. It's difficult not to admire and be pretty excited about the accomplishments of the chemical enterprises over the last 180 years. Chemistry's done a lot of amazing things. We've got amazing drugs that cure sick people, agricultural agents that feed the hungry, textiles and materials that clothe people in harsh conditions, materials, electronics. Man, we've done a lot of good. But when you reflect upon how we make those materials, we still heat things under high temperature for the most part, apply high pressures during manufacturing, and use solvents and reagents that have, questionable impact on human health and the environment. Now, if we look outside the window and we look at nature and we look at cells and organisms and tissues and leaves and trees and bugs and bees, we see that nature outperforms us humans in molecular diversity and complexity, but does so not only at the molecular level in what it achieves, but in how it does it. All manufacturing, for the most part, is at room temperature. All manufacturing in nature is mostly run in the ambient conditions, and for the most part, water is used as a solvent. So not only does nature outperform us from, what it achieves, but more importantly, how it achieves it. And so this is not a new concept. A lot of people have commented and made these observations. But the next thing is to say, why? Why is it that nature does such a good job? If we can understand mechanistically what's going on in nature, maybe that provides some insight. And so the epiphany that I had in the 80s was, simply put, a thermometer is a molecular speedometer. Now, what do I mean by that? What I mean by that is, if you think about how we teach and do and understand organic chemistry, molecular reactivity is based on specific geometries. We learn that an SN2 reaction requires a 180-degree approach of the nucleophile to displace the leaving group. We learn that when we have an electrophilic aromatic substitution reaction, the incoming electrophile must approach the pi cloud at a 120-degree angle that's antiperiplanar to the system. So we know that happens. So therefore, most molecular collisions don't have the right geometry. When the molecules are banging into each other, chemical reactions don't happen. So most of the time it doesn't happen. So what we have learned over the last 200 years is that by heating reactions and putting them under pressure, we increase the molecular velocity of the molecules and thus the frequency of collisions. Now, while this increases both the non-productive and the reaction-producing collisions. And so the reason that we heat things up, the reason that we put things under pressure, is to increase the frequency of collision so that statistically we get more of the reaction-producing chemistry to happen. So while I was at Polaroid, I looked at that and I said, isn't it interesting that in nature there is never a reactive collision? If you think of all the chemistry and biochemical processes that happen in cells and tissues and leaves and bugs and bees and all of that, you end up coming to the realization that there's never really a dilute solution. Everything in nature, for the most part, is a semi-condensed state with tissues and gels in which molecular movement is not quite as free as in solution. But what ends up happening is that in nature, molecules, for the most part, first form some kind of a complex or assembly that orients the reactive orbitals. So the molecules end up in nature snuggling up first so that the orientation is such that the geometric approach is restricted so that then and only then the chemical reaction happens. Okay? And in the 80s, I started calling the intentional molecular level biomimicry, I started calling that non-covalent derivatization as a way to lower the temperature of a manufacturing process, as a way of increasing the yield and doing different things to improve chemical synthesis. Well, at Polaroid, and again, I'm sure a lot of people on this call know the story, so I'll go through it quickly. We had to get EPA approval for some of these inventions of non-covalent derivatization. I encountered a friend that I had grown up with who was a fellow student at UMass and grew up in the same city as me, Quincy, Massachusetts, Paul, and asked us. One thing led to another in this discussion of non-covalent derivatization, and Paul's work, in green chemistry at the EPA had us get together and write this book, Green Chemistry Theory and Practice. Now, again, when one looks at this book, one comes to the conclusion pretty quickly that there's nothing really earth-shaking in this book, that this book doesn't have any really startling ahas. It's kind of simple and straightforward. And so anyone really could have written this book. It just so happens it was Paul and I at the right that did it. But what essentially it said is that at around 1990, 1991, the U.S. Pollution Prevention Act had passed. And there were lots of people talking about measuring, monitoring, remediating, recycling, and looking at pollution from okay, we got this stuff, what are we going to do with it? When we look at non-covalent derivatization, we reflected upon, isn't it interesting that that is an intentionally designed system that is better for the environment, that is less toxic, and therefore better for a variety of different reasons. As a student going into chemistry for 4 years of undergraduate and 3.5 years of graduate school, never really had a lot of discussion about making things non-toxic, making things environmentally benign. I'm sure that at some level people think about it, but there's no science, there's no journals, there's no meetings, there's no textbooks, there's no way for information dissemination so that we can do what science does and grow incrementally from other people's work. And so green chemistry was created to provide a forum, just like analytical chemistry or nanotechnology or whatever, as a way to focus a set of principles so that people could communicate and share each other's ideas. And so the intent was for green chemistry to be a science that would allow what the chemical enterprises to start creating pedagogy and work around this so that it can be more integrated and developed. And so from my perspective, the really most significant component of that book is the 12 principles of green chemistry. Now, if someone else wrote these, they may look a lot different. They may be a little bit different in number or something like that. The way that I look at the world, I am very comfortable with these 12. They've been around now for 18 years. And every once in a while, someone comes and says, you forgot blank. And I say, well, no, it's actually in this one here. Or someone says, why don't you combine these? And, again, the presumption is I may or may not be right or wrong, but I feel very comfortable that this has survived the tests of time, that this is not only molecular synthesis at the covalent level. Remember, this was created in non-covalent derivatization, which was actually, what you could think of as formulation sciences. And so when someone says, well, gee, I don't make molecules, I don't do green chemistry, they're kind of missing the point. Anything involved in the manipulation of molecules is involved with green chemistry, period. Whether you're studying it, analyzing it, making it, formulating it, coding it, eating it, so it's well, maybe not eating, but you get the point. So from my perspective, green chemistry as a science, for it to have impact and to be successful, it's not enough to just be environmentally benign. Okay, although that's the whole focus, is that environmental benignness, if you will. The perspective is that if someone invents some technology that's better for the environment, but it still doesn't work, no one's going to use it. So for green chemistry to be successful, it also has to have superior performance. No one wants a cleaner that doesn't clean just because it's environmentally benign. So you've got to have better performance, and society has demonstrated it's willing to pay a little bit of a premium, but not too much of a premium, and so that the economics must be consistent. If the technology is too expensive, then people won't buy it and it will not accomplish its goals. So the only way for green chemistry to ultimately be successful is if the technologies are safer, have superior performance, and superior cost. Now, the only person who can deal with those issues is the inventor in the first place. When he or she goes in the lab and starts inventing something, that's really the only time that you can have impact, because once the technology is invented and it's in the market, you're kind of stuck. So green chemistry has a very specific focus on the design, not so much what you do with it afterwards, okay? And so that's the distinction. So how does this relate to teaching of chemistry? If, you know, and again, I don't want to imply that non-covalent derivatization is the only form of green chemistry. It is a tiny component of green chemistry. People working in catalysis, people working in solvents, people working in surface chemistry, people working in all different aspects of material science have an equally important role in green chemistry. So I don't want to mislead people into thinking non-covalent derivatization is somehow a special form that is better for green chemistry. It just happens to be what I do. And so that's what I can only speak from my experience. That's what I do. But when we take a step back and think about teaching from a bigger perspective, you know, if you reflect upon all the materials that are available in society, the ceiling tiles, the carpeting, all the different things we can buy, the electronics, the medicines, the things like that, I would argue that maybe 10% are truly benign. And 90% of the things out there can be improved and need to be improved. Maybe just a little, maybe a lot, but there's a lot of improvements that need to happen, okay? And then I would say that there's this process called alternative assessment, where someone goes and searches the supply chain to try to find something better. And there is a moral and ethical component to this that manufacturers, that brand names, that you know, retailers should always be vigilant in trying to find the best technology available in the supply chain. But it is my assessment, and this hasn't changed in a long time, that over 65% of the technologies, it's not that they're available, it's that they haven't been invented yet. And that is, I think, the most important take-home message, is that this isn't an epic battle of good and evil, that companies have better technologies that they're suppressing. Because remember my definition, superior performance, superior cost, and oh, by the way, it's better for the environment. Now, when I say superior cost, that's all the capitalization and the cost that goes into retooling a factory. So my assumption is if you have a technology that has superior performance and superior cost, the fact that it has an environmental benefit will not be a hurdle to its adoption. So the only hurdle to green chemistry, in my opinion, by that definition, is the invention in the first place. And so at the end of the day, this becomes critical that we educate future chemists and existing chemists to do that, to invent these types of technologies. And so I look at this and I say, what better time in the history of humanity to be a chemist than today? We have important work no matter what we want to do. If we want to do medicinal chemistry, if we want to do agricultural chemistry, if we want to work on polymers, if we want to work on cosmetics, that day job keeps us busy. But upping our game to make these technologies switch from traditional technologies to green chemistry technologies now has such a bigger purpose. Why is it that every middle school student, every high school student with eyes the size of silver dollars and want to save the world, if you ask them what career they want to go into, it's unlikely they're saying chemistry. And you got to wonder, why not? What are we doing wrong in communicating this? And so our role as educators need to be a little bit better at making sure that people understand the opportunity here. And so I see the world in a sense of a toolbox. Okay, we have a toolbox with a bunch of drawers. And in those drawers, there's all kinds of different chemical transformations. Carbon-carbon bond forming reactions, oxidations, reductions, you name it. I would argue today in 2014, this toolbox, while not completely filled, is pretty filled. And if we can conceive of a molecule and it doesn't violate some fundamental law of physics or chemistry, given enough time and resources, we can probably make it. However, if we imagine a green chemistry toolbox that has those same drawers, but now those transformations are non-toxic, environmentally benign, and superior performance, superior cost. I would argue, as I did on the previous screen, that that toolbox is 90% empty. And so this is a call to arms to say, let's fill this toolbox. Let's get an army of undergraduate students, an army of graduate students, an army of people in industry to do it. But here's the catch. I feel that over the last 18 years, the business case for green chemistry has been heard loud and clear. People understand the cost benefit of a sustainable technology. People understand the consumer appeal to an environmentally beneficial technology. But the problem is that they haven't been invented. What is a company to do if they open a green toolbox and they don't find the tool that they're working with, they're looking for? They can't. The way our economy is set up, they can't stop everything. Let's invent a new technology. You can't plan an invention. So what they must do is close the green chemistry toolbox, open up the traditional toolbox, figure out what the regulatory costs will be, what the exposure costs will be, the liability costs, how many gloves and masks and goggles and scrubbers and filters, and they'll have to go business as usual with the less preferable technology because they're in the business of meeting consumer demand and getting a product out the door. They can't, they don't have the resources or the ability in the current climate, which we'll talk about in a little bit, to invent. So it is really up to institutions and academia, undergraduate and graduate, to play that role, which is not a new position for it to be in. It's just got a new set of requirements. So I think it's important from a pedagogic perspective for us to understand, and again, I put my disclaimer, this is the way I look at the world, all right, that how does green chemistry fit into the bigger picture of sustainability? All right, and again, I apologize if there are people on the EPA on this call. I'm not being mean, but it bothers me a little bit that on the US EPA website, the statement green chemistry is also known as sustainable chemistry is written. Sustainable chemistry has been around for a real long time. Green chemistry is not sustainable chemistry. There are great people who have been working in the field of sustainability chemistry for a long time. It would be presumptuous to assume that green chemistry somehow has subsumed that whole field, because sustainability is a big picture concept that covers many aspects of society. Okay, you can think about the word sustainable and you can put any word you want after it. Sustainable economics, sustainable agriculture, sustainable education, business, chemistry, engineering. There's a million ways of coming up with that. Chemistry is the subset that deals with materials and molecules. Chemicals policy, remediation, exposure, green chemistry, water purification, alternative energy. There's a whole bunch of ways of doing that. Green chemistry I see as a subset of sustainable chemistry, where it's not dependent on the application. Water purification is a sustainable technology. Solar energy is a sustainable technology. But if the solar panels are being made with toxic materials using a large amount of energy, it isn't the green chemistry technology. So green chemistry is application agnostic and looks at how the material is made, the solvents, the catalysts, the feedstocks, the toxicity, the persistence, the energy. I have a bias. There are 12 principles. There's 12 ways to divide that up. That's the point, is that green chemistry, it doesn't matter if you're making a solar energy device, you're making a water purification membrane, toothpaste, or a comb. It's green chemistry applies because it's how it's all being made in its entire life. So we need So when we teach chemistry, another aspect of this is we need to challenge some basic vocabulary and assumptions when we talk about chemistry. All right? We all bemoan the lack of appreciation of the general public understanding chemistry, but we also got to up our game amongst ourselves as well and really look at the way we communicate. You go through the literature. Let's, I joke here, let's talk about nothing. Here's something that breaks my heart. All right, there's two issues with the use of free and zero. When someone says that a product is chemical-free, what does that mean? Think about that for a second. And what disservice are we doing to society to play on their emotions and fear by putting on the label of a product chemical-free? Okay, you got to just wonder, okay, if there's no chemicals in these containers, what is in the container? Is it a thought? Is it an idea? Is it imagination? You know, and so we really got to really be a little bit better about this language. But more importantly, the word free, anything being free, is it really possible? Okay, if anyone's familiar with some of my history, several years ago, there was a lot of information about bisphenol A in cash register receipts. I was written up in this famous journal and quoted on the same page as a cat pushing a shopping carriage. John Warner reveals bisphenol A in cash register receipts. All right, and that took off. Now, here's an interesting thing for you to think about. If a company that sells cash register receipts, thermal imaging, says, we have put no BPA in the added coating, and then you grab that coating and you run to some really good GC mass spec, you will find BPA. But what's interesting is that company honestly and sincerely didn't add it. But because BPA has been around for so long, it's gotten as part of the paper stream, and that you cannot possibly have a piece of paper now that doesn't have trace amounts of BPA. It's tiny amounts, but no one put it in there. It's just now it's there. So what does BPA-free mean if we can't honestly get it out of ink? Is it ever achievable? Imagine that I had a 55-gallon drum of water, and I put a teaspoon of sugar in it. All right? That teaspoon of sugar is 10 to the 21 molecules of sugar. It's a lot of sugar, but it's already only 1.14 ppm of sugar in that 55-gallon drum of water. If I took 1 grain of sugar, that's now 10 to the 17 molecules of sugar. That's still a lot of zeros over there, and that's already down to 50.6 parts per trillion. If I took a nanogram of sugar, what arguably is the smallest amount that we can imagine, that's 10 to the 12th molecules of sugar, that's still 176 billion molecules of sugar, our ability to measure molecules stops about here. So when we say that a product is free of a molecule, what we're really saying is we can't detect it. But as our technologies improve, people are going to come out and say, well, wait a minute, we did find it, but is it because analytical sciences have improved, or you know, or is it some cloak and dagger lie? And I think what we're going to find is that as technology gets better and better, more things are going to appear, and we need to allow society to understand that zero is impossible. That nothing, you know, I bet that in whatever room you're in right now, wherever you are right now, if you list 50 or 60 really scary, dangerous molecules, if you could measure down to where that yellow rectangle is on the slide right now, I bet you in the room that you're in right now, there are molecules of the most nastiest things that you can possibly imagine. It's just our ability to measure them is not there, and so for all practical purposes, we assume it absent. But we as science educators need to keep reminding ourselves that this is a Heisenberg principle issue, and that we are influencing our interpretation of the results by the ability to measure. Okay? And so I'm going to fly through the rest of the slides because I want to have time for questions. When we talk about inventing chemistry, I'm going to do these slides very, very quickly. I was asked once to talk about innovation in chemistry for Fortune magazine. And this is how I presented it. They said, John, what can you tell us about innovation after your 30-something years as an inventor? And I said the first thing was all innovation begins with science fiction. If true green chemistry is an invention problem and we need to invent more, you got to realize that the first thing we got to do as scientists is write science fiction, right? If we are inventing something that doesn't exist, the very imagination of that is in the domain of writing science fiction. Would our students, if we were talking to a group of our students, see themselves as science fiction authors? Well, in fact, if you're going to be an inventor, you must, by definition, first write science fiction, then hopefully someday in the future turn it into science fact. But is our education system promoting that kind of thinking? The second one, innovation happens not within the field of focus, but at the periphery. we got to realize that there are so many different ways of looking at technologies and science that the harder you look, sometimes the less likely you are to invent. If you think of the role of serendipity in the history of science, I think we don't admit it as much. We end up retelling the story as some heroic, insight. But there are so many examples of someone trying to solve one problem and accidentally stumbling upon a solution of something that they weren't even working on. As we have become more and more advanced in our instrumentation, I would argue high throughput technology is reducing the chance of these kinds of inventions and discoveries from happening. Now, I'm not saying that there isn't a role for high throughput technology, but not too much in the invention space. And so we really got to think about that a little bit. The third one is a little bit controversial, but encyclopedic knowledge inhibits innovation in the absence of intuitive knowledge. And what I mean by that is you need, we value that which we can measure. And we can measure a student's ability to have mastered precedent, to be able to quote facts of what has happened before. But we haven't really done a good job at measuring someone's ability to intuitively predict something in the future. And imagine any organization of people that are talking about, gee whiz, let's go do this. And everyone says, hey, wow, that's a great idea, let's do it. And one person in the room says, wait a minute, 3 years ago, Professor so-and-so tried that, and it didn't work. All of a sudden, that person becomes the stopper of everything. And although and so our society right now hasn't quite figured out how to balance that. And we need to think about how to reinforce the imagination to list reasons why something won't work. And it takes a heck of a lot of courage to try to do something. And more often than not, I would argue that big companies invent solutions all the time. They have the statistical chance of having brilliant inventions, and I bet every day they have amazing inventions. But they also have a statistical chance of some dude being at a table, putting their hand to chin, saying, wait a minute, this might not work. And so statistically, there's a better chance that some big company is going to kill an idea because of that process. We need to evaluate our reaction to that. The fourth one is our ability to innovate is simultaneously proportional to wisdom in the tolerance of intellectual risk. Now, use as an example of this, a couple years ago, Daniel Shechtman got the Nobel Prize for quasi-crystals. If you look at all of the literature and all the news reports afterwards, it's all about how he came up with this idea, he gets kicked out of his university, gets fired, he's disgraced, nobody likes it, and 15 years later, through sheer force of will, he ends up getting the Nobel Prize and showing the world that his idea was right. Now, I look at that and I say, what a condemnation of the field of chemistry. How many brilliant Nobel Prize-winning ideas do we flush down the toilet every day because the person's personality doesn't have the persistence to fight against the forces? We got to really step back and say, what does it really mean to be a diverse organization, and how do we really measure things? If the only way we measure things is by their embeddedness in precedent, we will never innovate. And so we've got to realize that risk comes in many ways, and we need to come up with ways of teaching that. And then the final one is innovation is orthogonal to complexity. Some solutions have complex answers. Some solutions have simple answers. Doesn't matter. The answer is the answer. And sometimes we get caught up with the need for simplicity or sometimes the need for complexity. It doesn't factor into innovation. So my next chapter about investing is very quick. And again, so many of our students are going to end up getting jobs working in industry or working in investment fields that it's important to think about this. When we do science, what do? We explore something, we then try to understand it, and then we put parameters around it to try to predict it, and we call that basic research, to understand a phenomenon. Well, you know what? In business, we do the same thing. We explore a product, we look at how it interacts in a market, we poke at it to see how it behaves, and then we try to change it up to see if we can make a better product. So those two things, remarkably, are more similar than we might think. Then we hope that they come together, we create some kind of prototype, and then we use something called a technology incubator to commercialize that successful technology. And this is a tried and true model that most universities, most cities, most states, most companies have what they call a technology incubator, where they take a prototype and try to bring it to market and commercialize it. Now, right now in the U.S., the statistical chance of success is 1 in 10. Those are dismal odds. And I would argue that those odds are so bad not because the people doing it aren't skilled and good at what they do, but frankly, we've got really bad prototypes. And what universities need to do is start looking at themselves less as an incubator and more as a technology greenhouse, focusing on the idea to prototype and trying to do collaborative work with people in the business community, with people in the sustainability community, to make sure that the prototypes are better, that we've built in business reality into that prototype and sustainability, because once the investment has happened and the momentum to market is happening, it's almost impossible to say, wait, let's go back and reinvent it. So what ends up happening is it's seen as a failure and it stops. We need to be better at that. And that's part of our education, is to really look at that process. Finally, with managing chemistry, what I'm talking about here is chemicals policy. And it's not a one-person show. We all got to look at this process. And I'm not going to go into great details, but you'll find that chemicals policy informs what we should be thinking and doing. That the field of toxicology and environmental health sciences has to come up with better metrics and ways of measuring success. That alternative assessment has to always be evaluating products and processes. And finally, green chemistry's role is when there isn't a better process to get in the lab and invent it. No one of these things is more important than the other. And what is really hurting the future at this point is a lack of appreciation, knowledge, or even basic vocabulary of the other circles. And I think it's incumbent on us, I believe, to at least allow some part of our education to make sure that, hey, if you're going to in the future be inventing stuff, make sure you understand the yellow, the red, and the blue as much as the green. And so that's just, again, my perspective. All right? And so from that perspective, what I call the elements of safer chemicals policy comes into play. Governor Schwarzenegger's administration asked me to chair the Chemicals Policy Initiative in California. I spent 18 months on their Green Ribbon panel being the science co-chair. I ended up resigning from that for a variety of reasons. One, I'm a chemist and not skilled at doing that. But I was pressured into saying, well, John, what would you do if you didn't like what we were doing? And I came up with this, and I submit this not as a solution, but as a thought piece for people who are involved in chemistry to think about. The first element, right now, when we talk about safer chemicals, we want to ban lists of molecules. But what we really should be doing is focusing on the way we evaluate them. There are people who feel that certain molecules are toxic. There are people who feel that certain molecules are safe. Now, while we debate the molecule and the intentions of those people, we rarely debate the serious reality, which is one of them has a bad assay. We need to be focusing more on the assays, because every time someone just comes up with a replacement that isn't what we banned, next thing you know, we find it's just as toxic. Man, that's not good. And so if we focus on how we measure safety, that will help a heck of a lot. And by doing that criteria, it allows one to anticipate what it will take to invent that solution. The second element is we've got to stop looking at molecules and look at full products. Because when we manufacture any product, the list of ingredients is almost irrelevant. Many of them vanish during the manufacturing process, but more importantly, as chemists, we fully appreciate new molecules appear during the manufacturing process. So just looking at the list of ingredients isn't terribly relevant. So some ingredients disappear and some ingredients appear. But more importantly, if you do the product, there's no trade secrets. You're not revealing the name of the chemical that's that's a problem. You're just listing the product itself. Now it is incumbent of the manufacturer of that product to figure out what molecule is causing it. But it kind of simplifies communication. And then the final element is we should stop using the word safe and dangerous, and instead, if we have a bunch of assays, report the quantitative data of that assay. If I go to the supermarket to buy food, there isn't a label that says good, bad from the government. If I want to eat only protein, the label must give me the information that says how much protein. If I want to eat only carbohydrates, it has to give me that information. So it doesn't tell me what's good or bad, but gives me the information to make my own decisions. Well, if we had 10, 12 different assays that all products were evaluated by, and we reported the score on the cancer assay, the score on the endocrine disruption assay, the score on the global warming potential assay, whatever, then that score, people could compare different products and realize that 0 never happens. And so that when someone says something is safe, it still actually has a number. And society needs to appreciate that it's all relative. And so something is safer, but you'll never see many zeros. And so then NGOs can help do the great job that they have been doing, but instead of saying, hey, don't buy a product that has the following molecule in it, they can say, don't buy a product that gets a score of such and such or lower on a product. Now it's more science-based, and it allows all the systems to work together to come up with alternatives. So again, I apologize for rambling on and all these different things, but I know that there's a diverse group of people on this call, and I just wanted to give a bigger picture of how green chemistry and the impact of green chemistry and all of this goes far beyond just making molecules. Now, green chemistry is the part with the people doing the beakers and flasks making the molecules, but we have a larger role to play, and we need to train our students to be better prepared to communicate all up and down this process. Thank you for listening to me.
Great. Thank you, John. That was fantastic. A great start. I have some questions coming in here, so I wanted to start with just a quick clarification question. When you mentioned BPA, did you mean that it exists in the ink on those papers or on the paper?
Probably both, but most likely in the paper. You see what's been happening, and again, we have done some work in this, and so I haven't done extensive work on this, but if you just think about it, people have been putting their cash register receipts out with the paper has been recycled and commingled, and so obviously over the years, those cash register receipts have been ground up, pulped and papered, and so that the BPA and trace amounts have been accumulating over time. Now, it's probably at a very, very, very low level, and so, you know, it's probably nothing to be alarmed at. But from a scientific perspective, if you say it's not there, it's probably inaccurate.
Great. All right, and I'm going to try to find your recent publication, and I'll put that in the chat box there too.
Yeah, I want to put I'd like to put a plug for the work that a great group of people have done. Pete Myers and friends published a paper in the journal Green Chemistry describing typehead, which is an evaluative process for endocrine disruptors.
Yeah, great. And here I'll just give you the. So here's the next question. How is the technique of non-covalent derivatization practiced in the lab? Is there a good example?
There's lots of examples. The first example that comes to mind is in medicinal chemistry. In pharmaceutical sciences, many times a molecule that is not orally bioavailable, so that it's not very effective because it's not being bioabsorbed, non-covalent derivatization can be done in the formulation process to increase its oral bioavailability. And so that's where a lot of this initially made a lot of headway. But obviously the opposite of that is true too. If a material is bioavailable and you don't want it to be bioavailable, you can use non-covalent derivatization to inhibit. And so there's a great deal of examples in that. You know, in photography, in many polymer systems, when you have a pigment or a material that's phase separating out, people use non-covalent derivatization to help, you know, compatibilize it. So yeah, there are hundreds and hundreds of examples.
Okay, great. And here's a question, more, I guess, a broader question. When do you think, green chemistry should be covered in chemistry education? General chemistry, more advanced courses? Where do you think that goes?
You know, if you ask that question of me of organic chemistry or analytical chemistry or physical chemistry, I would say, it's kind of a tough thing. Obviously, to teach a subject, you need to put boundaries around it and have some kind of pedagogic body of knowledge to teach it. But just because we have a textbook called analytical chemistry, I would argue no analytical chemist on the planet is good at their job if they don't know physical chemistry, organic chemistry, and other parts of chemistry. Well, the same thing has to do with green chemistry. That green chemistry is not a standalone concept, as is either of those other ones. Now, as time has evolved, some universities have chosen not to have courses in analytical chemistry and said, well, we cover it in freshman and physical. And some say that's impossible. Of course we have to have those classes. Some universities don't have inorganic classes, but instead integrate it. Same with biochemistry. I would be presumptuous to say that there is a right way to do it. It has to be done by the way that that university, that department wants to do it. If they want to do a standalone class, then they should do a standalone class. If they want to integrate it into the labs, they should integrate it into the labs. If they want to do it as an integration into some of the lectures, everyone should be free to do it the way they want to do it. But what we need is a community of people, as the Green Chemistry Commitment is doing, that we can share best practices to help people not have to reinvent the wheel. So if a university is contemplating bringing green chemistry into the curriculum and they log into the commitment, they can see how different universities have done it and help them, get faster and better and quicker. I personally, just to be clear, I feel it should be a one-semester standalone class. To me, I can't imagine anything in the chemistry curriculum more important. So given my brothers, I would have it as a standalone class, but that's just me.
Great. We're going to answer just a couple more questions, but I just wanted to pause for a second to announce the winner of the textbook. That's Kendall Hannon. So Kendall will be sending you an email to gather your information so we can get that out to you. So congratulations to Kendall Hannon. Okay. Back to trying to answer some of these questions. Just real quickly, what role can students play in promoting green chemistry?
Students play a massive role in green chemistry. The faculty are so busy. It's not an easy job being a professor. You've got demands to do teaching, you have demands to do research, you got demands to do support, in different parts of the administration. And it is just such a tireless job to say, gee whiz, and I'm going to now introduce all of this stuff that isn't already in the curriculum. It's really hard. But when a group of students start saying, hey, we want this, don't ever underestimate the power of that. There are probably faculty sitting on their edge of the seat wishing they had the support of their administration, wishing they had support of people who have the ability to allocate resources. And so by being vocal, by asking in a polite and non-confrontational way to say, hey, listen, we really want this to be part of our curriculum, don't underestimate the power of that.
Okay, great. A question about your assay approach. When you look at assays and a molecule is still present, but in life cycle assessment, at one point the product decays, such as the molecule is released, doesn't it still make sense to need to know that the molecule is there? Does that make sense?
Well, I guess the thing is, remember, the way I defined assays is wide open. A group of people would have to come together to say, what assays? And if one of the assays is an environmental degradation assay to evaluate what happens under certain conditions over certain time, then that would be a very important assay. Again, I'd be presumptuous to pick and choose what those assays would be. Smarter people than me would have to come up with it. So absolutely, if the group felt, and I agree, that understanding the consequence at the end, but I would rather that be a measured piece of data, not something that is projected. And so if you took something and stuck it under controlled conditions for X amount of time and conditions, and then measured the toxicity, that might be a way of doing it. But again, I don't have the answers. I'm suggesting a group of people who are smarter than me put together what those assays would be. I have my guess, but they're probably not that good.
Okay, great. A question about from a faculty member here. I'm interested in green chemistry as a standalone class that John mentioned. My question is, do you have particular topics that one should address or work on each principle per class session? Do you have sort of a framework that you suggest?
So Amy and I have taught what we call mechanistic toxicology and environmental health sciences a few times at Simmons College. And we would be happy to share the curriculum that we came up with. At UMass, we had a green chemistry PhD program where we had a full semester of mechanistic toxicology, a full semester of environmental mechanisms, a full semester of law and policy, a full semester of green chemistry, principles. So we'd be happy to share those syllabi, and they're probably on the web of Beyond Benign already. I would, so I have my suggestions of how to approach it, but I would look at my university, look at my faculty, find out what gifts and skills are already incumbent and build much of the course around them, and then bring in from the outside what's missing. But I would try to have the personality of the department in the college be as visible as possible, so it doesn't feel like an outside thing, but it really feels like something that's a commitment of the people in the department and at the university.
Okay. Excellent. We have, I'm going to try to get one more in real quick. Synthetic biology teaches biological systems to produce new chemicals. Is this considered related to green chemistry?
Absolutely. The issue with a lot of biotransformations is, for the history of synthetic organic chemistry, we have celebrated high-yield reactions that are easy to purify. So at the end of the day, a good reaction not only makes a high yield, but you distill it, you filter it, you do something to get that material out. In biotechnology, what we're finding is we get high yields of material, but we have a lot of what I amusingly call biogoo that comes along with the process. And so while we have an excellent synthesis, the frontier is to come up with better separations technologies to pull the molecules out in high purity. So one issue is we've got to come up with higher, ways of, more cost-effective ways of purifying the material. But in a much bigger picture, and it goes back to my original stuff about non-covalent derivatization, we need to rethink the whole process of Six Sigma, and maybe accepting an impure molecule that has a Gaussian distribution that's knowable, and using materials that aren't 100% pure but knowably have a portfolio. Maybe that's really the future of manufacturing, but we're certainly not there yet.
Okay, and one last quick question. This is coming from someone with an occupational safety and health background, so they gave us a little warning here. If vocabulary is important, and I agree that it is, why use the word safety, which is really about acute effects, rather than health, or something that indicates longer-term effects?
Well, I guess I wouldn't want to pick one over the other. Obviously, even my communication is flawed, and so I fully appreciate that the way we communicate is critical, and so absolutely. And so whether it's safety, whether it's sustainability, whether it's hazard, different scientists working in different fields as part of their research will probably gravitate to one or another of those words. The users of chemistry will have different proportions of interest in different ones of those words. But you're absolutely right. Not one. If this isn't a one-word thing, there are 12 principles of green chemistry. 3 of them deal with safety.
Excellent. Well, I'd like to thank you, John, for helping us with and presenting this first webinar of our series on green chemistry education. And thank you to all of you who tuned in for this. Please look on our website for upcoming webinars. Our next one is scheduled for November 19th with Dr. Jane Wissinger from the University of Minnesota. It's going to be a fantastic looking at organic, how green chemistry applies to the organic chemistry laboratory. And hopefully Jane will be sharing with us some of her latest and greatest green chemistry labs as well. So you can see the web link there, and feel free to also contact me directly with any questions, comments about the webinar series. Thank you so much.